So today we're going to go ahead and talk about conservation of energy. So we're going to talk about, there's two different systems out there. So there is a conservative system. And when I think of the word conservative, I see right in that word conserved. So, and reminder, conserved means that things like stay the same. Cool. So anytime something's conserved, you're kind of keeping it the same, the status quo, whatever that is. So in a conservative system, the total potential and kinetic energy stay the same. And one word that we'll oftentimes use as to represent the sum of the potential and kinetic energies is mechanical energy. So this word just means, so mechanical energy is, this is just the sum of all the potential energy and kinetic energy in a system. And again, for potential energy, I should use the symbol U, capital U. Cool. So like, let's look at a random conservative system. So let's say we have a system. So a system is some sort of like closed space, whatever you define that to be. So let's say in this system, there is 10 joules of kinetic energy. It could be like a candy jar, it could look at it, could be whatever. Let's say the gravitational potential energy is, let's say 40 joules. And let's say there's some spring potential energy in there, which happens to be 20 joules. Okay. So we know that the total energy is going to be the sum of all the energy. And in this case, it's just mechanical energy, sum of all potential and kinetic energy. So total energy is just sum of everything. So 10 plus 40 plus 20 is going to be 70 joules. Okay, so let's say we go ahead and move things around and there's some sort of interaction that happens. Remember, total energy is conserved in a conservative system. So in this case, let's say that we happen to have 0 joules of kinetic energy after everything was moved around. Gravitational potential energy, let's say that turns out to be 60 joules. Let's think about what spring potential energy would have to be. So we know that the total energy still has to be 7 joules. So all these energies have to equal 70 joules. So spring potential energy would just be 10 joules. Cool. So like a statement to kind of explain this or show this is that the energy initial will always equal the energy final. And that goes along with that statement that no energy may be created or destroyed. It always stays constant. It is going to be conserved. Okay, so we have a conservative system. Let's go ahead and talk about the opposite, a non-conservative system. So this is when we are going to add friction into the mix. So non-conservative system is we will add friction to the mix. And the reason why it is non-conservative is because you cannot get back like friction energy. Like that is going to be lost to the environment. So in this case, the total, if I can write, total kinetic and potential energy do not stay the same from the beginning to the end. Cool. So let's go ahead and do a little example. So let's say we have the same kind of system. So there are some energies here, okay? And let's say the total energy, let's say, is still 70 joules. And we have a variety of different, like, kinetic, potential, spring, just like last time. So if we do, we'll do 2 examples. So if the work is going to be, and I'll do it in a different color. So if the work is going to be positive, we add energy to the system. So we are giving the system more energy. So energy is transferred to system. Okay. So if work is positive, we're going to add energy to the system. So in this case, let's say like, I don't know, like we do some work on something by like raising it up higher. We could increase the total energy, let's say 20 joules. So we were starting at 70, we do 20 joules of positive work. The total energy would be 90 joules. So that's one example. Or let's say, I'll do it in a different color. Let's say the work is negative and we take energy from the system. So if we take energy from the system, I think of that as like a good example is like work. So it's like transferred from system. I'm sorry, a good example is like the work done by friction, not just like work. Work could be either positive or negative, but work done by friction is a good example of negative work. So then the total energy, let's say we take away 20 joules of energy. Friction makes us lose energy, so the total energy we'd be left with is 50 joules. Cool. So let's go ahead and just write an equation to represent this. So we know we'll start with some sort of energy initial. And then what I think about is we plus or minus work other equals energy final. And actually, I'll just go ahead and say plus because we'll know, like if we're using like the work due to friction, we know that that should be a negative because it is taking energy away. So we'll just put in negative whatever. And like another example of work like done through a system or negative work is like the heat lost produced by friction or other types of things. In most cases that we talk about this year, the work other will be like a negative quantity, like friction taking away energy. Cool. So we're going to go ahead and talk about conservation of energy, like a recipe for solving all problems, and then do an example problem together. Okay. So we're going to go ahead and solve a problem now. Okay. So we'll follow this recipe. So first thing we do, always read the problem first, and then draw a picture unless there's already one given. Luckily in this problem, there is already a picture. Okay, so we're done with step number 1. Now what we're going to do is pick a convenient reference point to designate where the gravitational potential energy is 0. Okay, let's look at this problem. So we have the 2 kilogram block and it's pushed against the spring. So here's our spring with negligible mass and a force constant, or we could call that spring constant, K of 400 newtons per meter, compressing at 0.22 meters. Okay, so it's compressed to like this little point right here. Cool. When the block is released, it moves along a frictionless horizontal surface and then up a frictionless incline with a slope 37 degrees. So for A, we want to find the speed of the block when it reaches a point 0.3 meters above the ground. So I'm going to go ahead and draw that right here. So we want the speed, I'm going to draw it like right about here. Oh my goodness, I can't draw. Cool. So we want the velocity or speed right here when it is 0.3 meters above the ground. Cool. Okay. So again, for deciding where the gravitational potential energy is 0, the best bet is just the ground level where the object starts from in this case. So that's height equals 0. Now what we're going to do is we're going to identify 2 positions where you have some information or desire some information. So I'm going to say this point right here where we start, that's going to be point 1 where the spring's compressed. This point right here is going to be point 2. Okay, so now let's go ahead and think about what we know at those 2 positions. So this first position, we will label the types of energy at each position, and then also label any givens at each position. Okay, so this first position, the object is touching a spring, that spring is compressed, so it definitely has spring potential energy here. Okay, it's not moving, it's released from rest, so there's no kinetic energy. And the height at the first point is 0. It's just on the ground level, so no gravitational potential. Cool. Okay, so let's look at our next point, point 2. So right there, it's not touching a spring, so no spring potential energy. It is some height above the ground, so we are going to have gravitational potential energy. And then it is moving, has some velocity, so it is also going to have kinetic energy. Cool. So we go with what. And let's see, we already have some good old givens at each point. This 0.22 meters, reminder that's the x. Cool. So now let's go ahead and go on to step number 5. Use conservation of energy. Equate the total energy of position 1 to total energy of position 2. Okay, so energy initial equals energy final. So that statement tells us we're using conservation of energy. Point 1, we have spring potential energy. Let's go ahead and look at point 2. We just have gravitational and kinetic. And we are summing the total energies, so it's going to be UG plus KE. And again, this is an example of a conservative system because there is no friction in this problem. So there is no work due to friction. So we don't have to add or subtract anything extra in this one. Cool. Now let's just go ahead and write down our equations and plug everything in. So US is going to be what? 1/2 kx squared. UG is going to be mgh. KE is what? 1/2 mv squared. Cool. Now we went ahead and did that. Now let's go ahead and solve for unknowns. So, and put in all of our givens. So 1/2 what? K is 400. X is going to be 0.22 squared. Mass is 2. G is 10. H is 0.3. Plus what? 1/2 mass is, where is that mass? 2 times velocity we want to find. Cool. Cool. So I went ahead and did the math, and I'm going to get 1.92 meters per second for this final speed at 0.2. So let's go ahead and look at part B. And I'll go ahead and do part B in a different color. So for part B, how far does the block travel above the ground before starting to slide back down? Okay, so let's go ahead and draw it all the way up here. So we know at 0.2 it's going 1.92 meters per second. So it's only going to slow down as it goes from 2 to 1. Okay, and we know when something reaches its highest point, whether we're throwing it up the air or it's moving up a ramp, its velocity is going to be 0 for a split second before it turns around. And we're going to want to find this height h. Okay, so we'll go ahead and do the same steps as previously. Picture we already have done, step 1 done. We already know the ground level is our height 0. Let's pick 2 positions. Okay, so I'm going to choose the second position as, or this point right here, we're going to find the height as our second position. For our first position, we could use either of these 2 positions, 1 or 2, and it would totally work out. For easiness, I'm going to go ahead and choose 0.1 because we're only dealing with one type of energy right there. So that's going to be my 2 positions. Now let's go ahead and label the type of energy of each position. 0.1 we already did, just spring potential energy. Cool. 0.2, we know it's some height above the ground, so it has to have gravitational potential energy. Its velocity is 0, so that means it has no kinetic energy there, so we're just dealing with gravitational potential energy. Cool. Now let's go ahead and use our conservation of energy equation. So we know all the energy at 1 is going to equal all the energy at 2. So let's go ahead and again, energy at 1, we know we're just dealing with spring potential energy. Energy at 2, we're just dealing with gravitational potential energy. So spring energy is what? 1/2 kx squared. Gravitational potential energy is what? mgh. So we are left with what? 1/2 k is 400. X we know is 0.22 squared. Mass is 2. G is positive 10. Height we want to find. And I go ahead and get, when I plug it in, 0.484 meters. Cool, and that makes sense because, and again, we should always, sometimes I forget, do this at the very end, check units, reasonableness, special cases, all that good stuff. Because originally at 0.2 is 0.3 meters, but it was still moving. So to get to higher point, it needs to be more above the ground. So 0.484 meters makes sense. Okay, so now let's look at the last part. What is the total mechanical energy in the system? So again, total mechanical energy is just a fancy word for total energy. So total energy, and again, mechanical energy is going to be like all the potential energy and kinetic energy at one point. And we know that potential energy includes spring and gravitational, all that good stuff. So we could choose any little point we want to work at. We could choose 0.1, 0.2, or this new 0.2. I'm going to go ahead and just choose 0.1. So I'm essentially choosing this whole entire, oopsie, sorry, my K got deleted accidentally. Cool. I'm going to choose this whole point right here for my starting point. And this should be spring potential energy, sorry. So we know that right here, it is just 9.68 joules of total energy. So 9.68 joules. And that is going to be your total mechanical energy. If we were to choose another point, so let's go ahead and say we choose like 0.2 right here. Let's say we choose that point. We should still get, oopsie, sorry, I accidentally deleted some of my stuff. We should still get, when we add this all up, so if we were to plug in our 1.92 into here, we should still get 9.68 joules. Same thing, if we do over here and we plug 0.484 into here, and that point right here, we should get 9.68 joules because the total energy is being conserved in the system. We're not dealing with any friction. Cool. Thanks for watching.